So we're going to talk a little bit about angular momentum. If you remember the definition for linear momentum, we used linear momentum was just p equals mass times velocity. Technically, it was a vector. Not technically, it's a vector. So we can develop an analogous equation for angular momentum. And so angular momentum is given the designation L, the letter L. And if we use the rotational equivalent of mass, we have an I here. And if we use a rotational equivalent of velocity, we have angular velocity here. And so in one dimension, we just say L is equal to I omega. And so if you want to know the angular momentum of something, you can calculate that from its rotational inertia times the angular velocity. And so, for example, we could say, what is Earth's angular momentum? Right. If we assume the Earth is a solid sphere, then its rotational inertia is just 2/5 mr squared, which is 2/5 times 6 times 10 to the 24th kilograms, because that's the mass of the Earth, times 6.38 times 10 to the 6th meters squared, which gives us 9.72 times 10 to the 37th kilogram meter squared. And so if we wanted to calculate its angular momentum, we'd need to use omega, right? We need to multiply this by omega. Omega is equal to 1 revolution per day, right? The Earth rotates, or rotation per day. But then we want to convert it into radians per second maybe, and so it would be times 2 pi radians per revolution, right? Times 1 day over 86,400 seconds, right? That's 24 times 60 times 60, right? 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And if I evaluate all that, I get 7.3 times 10 to the minus 5th radians per second. This is a result we calculated previously, right? And so then I can calculate the angular momentum, which is 9.72 times 10 to the 37th kilogram meter squared times 7.3 times 10 to the minus 5th radians per second, which gives me about 7.1 times 10 to the 33rd kilogram meter squared per second. Those are the units of angular momentum. We don't really give that a name. And so that's the angular momentum of the Earth. So we're going to talk about angular momentum and torque. This is sort of still for rotational motion, but if you remember, for translation, in other words, for basically for linear motion, we had the force is equal to the mass times the acceleration, which is equal to the mass times the change in velocity over the change in time. But mass times change in velocity was just the change in momentum, and so the force was equal to the change in momentum over the change in time. And this is really the way Newton wrote it. For rotation, we replace force with torque, and we replace mass with rotational inertia and A with alpha, and so that gives me I times delta omega over delta t. But we already said that I times omega is the angular momentum, and so this is just delta L over delta t. And so this is how the angular momentum is related to the torque. The torque causes a change in angular momentum. And so we can just do an example. A disk what is its change in angular momentum? And so we can just grab this equation and say, we can say the torque is equal to the change in angular momentum over the change in time, or the change in angular momentum is equal to the torque times the change in time. This is kind of like an impulse type equation. Remember, we had the change in linear momentum is equal to the force times the change in time, and we call that the impulse. And so in this case, the torque is 25 Newton meters times 2.5 seconds, which is 62.5 Newton meter seconds, which is 62.5 kilogram meter squared per second. So we're going to talk a little bit about conservation of angular momentum, and we're going to do it very similar to the way we talked about conservation of linear momentum. We just said the torque is equal to the change in angular momentum over the change in time. And so we can talk about the net, the total torque, is equal to the change in angular momentum or the change in time. In other words, if you add up all of them, you'll see the total change in angular momentum over time. This would be for any individual torque, but here we're just talking about the total torque. And so we can say that if the net torque is 0, then the change in angular momentum over the change in time is just 0. And that means the change in angular momentum is just 0, or angular momentum final minus angular momentum initial is equal to 0, because that's what the change in angular momentum is, or L final is equal to L initial. Which means angular momentum is conserved. If you remember, angular momentum is equal to I times omega. And so when angular momentum is conserved, it's saying the product of these two is conserved. And so think about an ice skater. Whenever you see an ice skater, sometimes in ice skating shows, you'll see an ice skater spinning with their arms out, and they pull their arms in and start spinning faster. When your arms are out, your rotational inertia is large because your mass is spread way out. And remember, this depends on kind of mr squared, the square of the radius. And so if your arms are out, your angular momentum is large, and so your angular velocity is small. If you pull your arms in and reduce this number has to get bigger. And that's what happens to a skater. When they pull their arms in, by reducing their rotational inertia, they have to increase their angular momentum. That's why they start spinning faster. And this assumes, of course, there are no torques acting on it, but if somebody's spinning on ice, you're typically going to see very small torques. So we can kind of, it's like assuming they're frictionless. Okay, in this problem, we have a playground merry-go-round. MGR is merry-go-round. that has a mass of 120 kilograms and a radius of 1.8 meters. We're going to assume it's a solid disk. It's rotating with an angular velocity of 0.5 radians per second. 0.5 revolutions per second. What is its angular velocity after a 22 kilogram child grabs onto its outer edge? And so here's the idea, right? It's spinning here with omega naught, right? It's got whatever its mass is equal to. I'll have the mass for m, and then I'll call this the mass of the child, say, or something like that. So mass of the merry-go-round is 120 kilograms, right? The radius is 1.8 meters, and it's a solid disk that's spinning with this velocity, with this angular velocity, right? And then the child's going to jump on, just grab onto the edge, hop onto the edge, and go around with it. And you can probably imagine, this is kind of like a linear momentum problem. When they jump on, it's going to cause the thing to slow down because they have to gain some of the angular momentum that the cart had. But there's no external torques, because if you view the child and the merry-go-round as one item, then the forces between them are interior forces, and so they're part of the system, right? There's no external forces from outside the system, external torques. And so what we can say is, for this one, angular momentum is conserved, and so we can say L final is equal to L initial. And so what this says is I final times omega final is equal to I initial times omega initial, which we called omega naught, right? That's this number. And so the initial angular momentum is just the angular momentum of the merry-go-round, which is just 1/2 times mass of the merry-go-round times r squared, which is 1/2 times 120 kilograms times 1.8 meters squared, which is I initial equals 194.4 kilogram meter squared. Or that's, if I want to call that, I can call that I for the merry-go-round. Right, that's the rotational inertia of the merry-go-round initially. Omega initial, omega naught, is just equal to 0.5 revolutions per second. If I multiply that by 2 pi radians per rev, that's just pi radians per second, or we could say 3.14 radians per second. If we want to get our answers in radians per second, we could have left it in just revolutions per second if we wanted to. And so this is omega naught, right? And so this is the initial angular rotational inertia. This is the initial angular velocity. At the end, I final, this thing, right? That's I for the merry-go-round plus I for the child. Well, we already know what this is. We calculated it. It's there, 194.4. I for the child is just the rotation inertia of a child spinning at a radius of 1.8 meters. And so the formula for, we treat them as kind of a point mass, just at one spot. The formula for that is just mass of the child times r squared, which is 22 kilograms times 1.8 meters squared, which is like 71.3 kilogram meters squared. You can see that. And so now we have, now we can say I final is I merry-go-round plus I for the child, which is approximately 194 kilogram meter squared plus 71 kilogram meter squared, which is equal to 265 kilogram meters squared, roughly. And now we can go back to my conservation angular momentum equation. We can say, look, I final, omega final is equal to I initial, omega initial, or omega final, which is what they're asking me for. What is the angular velocity after the child grabs, right? is equal to I initial, omega initial over I final, which is the initial rotational inertia is just Im times omega naught over Im plus I child, right? And so that's 194.4 kilogram meter squared. I'll just call it 194 kilogram meter squared times 3.14 radians per second over 194 plus 71, which is about 265 kilogram meter squared. And that gives me about 2.3 radians per second. And so that's the angular velocity of the child after they grab on and slow the thing down.